Hello, and welcome to the static forces diagram practice worksheet. So we'll go ahead and start with number one. An object is hung from the ceiling with a single rope. Find the tension in the rope. So your first step is going to be to draw your force diagram. So we'll go ahead, we'll draw the rope. We will draw the 5 kilogram mass hanging below it. And now, we want to be able to draw the forces on this mass. Always, 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 there will be a force due to gravity. That force due to gravity is trying to pull this mass down. So then in order for the object to stay still, that means that the forces are balanced. And in this case, we're being asked to find the tension in the rope. So there will also be a force of tension pulling in the opposite direction. To calculate all of the forces on the object, well, there's really no way to find the tension without knowing that force due to gravity. And the force due to gravity is always equal to the mass of the object multiplied by the gravitational field strength, G. On Earth, this number is 10 newtons per kilogram, so I can say that the force due to gravity on this object equals 5 kilograms times 10 newtons per kilogram. And so this would give me a solution of 50 newtons. And then because the forces are balanced here, that also means that the tension in the string is 50 newtons. So moving along to number 2, an object is hung from the ceiling with 2 ropes. So find the tension in each rope. So again, we'll start with our force diagram here. Draw the 2 strings with the 5 kilogram mass hanging from it. We have rope 1, we have rope 2. We will still have a force due to gravity pulling it down, but now each string has some bit of tension in it. So we will have 2 tension forces that we're trying to find. So now we want to calculate all of the forces on this object. So again, we want to start the force due to gravity equaling the mass of the object multiplied by the gravitational field strength. And so this conveniently works itself out because you're dealing with the same 5 kilogram mass and then gravity on Earth. That doesn't change. We still come out with 50 newtons for that force due to gravity. And now again, the object is not moving, so that means that the tension forces have to balance out with that force due to gravity. So that means that the force of tension in rope 1 plus the force of tension in rope 2 have to equal 50 newtons. And because these 2 ropes are being suspended where they're not at an angle, we know that the tension in each will be the same. So if we divide 50 newtons by 2, we will get 25 newtons is the tension in each rope. So number 3, two objects are strung together. So this situation we're a little different, and we can break this problem up a number of ways. The first one, if I want to draw, I want to keep each mass single. So I want to find what it is for the 7 kilogram mass, and then I want to know what it is for the 4 kilogram mass. By doing it this way, we have string 1 and string 2. So by doing it this way, I know that there's again a force due to gravity trying to pull this mass down, and then the tension force which is keeping it from moving. And this is going to be the same for the 4 kilogram object. So when I want to calculate all of the forces, if I want to find the force of gravity, force due to gravity, for the 7 kilogram mass, I'll have to go that F of G for the 7 equals 7 kilograms times 10 newtons per kilogram to get 70 newtons. If I want to do it for mass, for the 4 kilogram mass, F of G was 4 kilograms times 10 newtons per kilogram. So that ends up being 40 newtons. Now how the tension works is that in the string it is only applied to what is below it. So that means that string 1, so string 1 up here, has to do with all the masses that are below it. So then the force of tension in string 1, so this is in string 1, has to equal 70 newtons plus 40 newtons to get a total of 110 newtons. String 2, right here, same as string 1, you just need to worry about what's below it. And because the 7 kilogram mass is not below string 2, we're just dealing with the 4 kilogram mass, which means that the force of tension in string 2 is going to be 40 newtons, because that is what the force due to gravity was on that string. So question 4, we have a person pulling a 50 kilogram desk with a 20 Newton force directed horizontally to the right, and the desk does not budge. So this means that here we'll draw this table. We have force due to gravity trying to yank this thing through the ground. To counteract the force due to gravity, we're no longer dealing with strings, we're on the ground. So this would be the normal force acting against it. We have 20 newtons of force being applied to the right because he's trying to pull the desk So we will have an applied force and then in order for that applied force to be balanced, because the object is not moving so the forces have to be balanced, there will be a frictional force acting against it. So now when we want to actually calculate these forces, we can work it through, and again we'll always start with the force due to gravity, mass times the gravitational field strength, so F of G equals 50 kilograms times 10 newtons per kilogram, and that will give us 500 newtons. Now because we have the normal force acting with it also, that 500 newtons is also the same for the normal force. So the normal force is 500 newtons. So now the second part, we have an applied force. And so this applied force, it tells us, is 20 newtons. So that force was nice and easy to calculate. Now this 20 newtons of force, because it's not moving, means that the frictional force has to balance that. So that is also 20 newtons. And that is how you do your static force diagram practice.